The next example we're going to do is finding the Maclaurin series for f of x equals 1 over 1 minus x. So at first when you start taking the derivatives, it might get a little intimidating because it gets very messy in the sense that, like we're doing the power rule over and over. But then some nice cancellation happens with the factorials, so it does end up balancing out. And if you're looking at the calculus review pack, you will see that this expression for the series is actually rather nice. So we're going to do what we did before, remind ourselves of the formula. And factorial. So we're going to start with taking some of the derivatives and hoping to establish a pattern. So let's think of f of x, really, instead of 1 over 1 minus x, let's just think of it as 1 minus x to the minus 1. It's a little easier, because then we can do the power rule. So the 0th derivative, which means the function without any derivatives taken yet, is 1 minus x to the minus 1. And if we evaluate that at 0, because again it's a Maclaurin series, so we're evaluating at 0, we end up with 1 minus 0 to the minus 1, which we don't even care about the exponent. We just see that the interior here is 1, and 1 to any power other than like infinity is equal to 1. So we get 1 for the 0th term. The next term is our derivative, so f1 of x equals, and now I'm going to apply the power rule. So we get negative 1 times 1 minus x to the negative 2. We're not done with the derivative though when we do this, because I applied the power rule, but I also have to apply the chain rule since we have this interior function of 1 minus x. And the derivative of 1 minus x is negative 1, because derivative of negative x is negative 1. So this actually all gets multiplied by a negative 1. These two negatives are going to cancel each other out. So this is really just 1 minus x to the negative 2, since the two negatives became a positive 1. So our first derivative, evaluated at 0, is 1 minus 0 to the negative 2, which again is equal to 1. I didn't write those in lines, so let's do that so I line them up better. So at this point you might be tempted to be like, oh, they're just all 1. Pattern is established. Don't do that unless you have a strong reason to believe that pattern is going to keep on going. And in this case, there's not really a strong reason to believe that, because when we do the power rule again, you see we're going to get a negative 2 in front instead of a negative 1, and that 2 is going to mess things up a little bit. So we're going to keep going and see what we get. The second derivative is, again, we use our power rule and chain rule, so negative 2, 1 minus x to the negative 3, and then we do the chain rule, so we have to multiply by negative 1, and we end up with 2 times 1 minus x to the negative 3. So what this tells us is that the second derivative, evaluated at 0, is 2. That was that 2 I was talking about. 2 times 1 minus 0 to the negative 3, which is just 2. The next derivative, we then get a negative 3 coming in front. So our third derivative of x. I'm not going to bother writing the negative with the 3 and the -1 again because we know we get two negatives and they cancel each other out and give us a positive. So I'm just going to write 3 instead of -3 with a -1 multiplied at the end. So what we end up with here is, well, we previously had this 2. Now we're multiplying by -3 and -1, so we have a 3. And then we have 1 minus x to the -4. Because I know where this is going, I'm going to write right here, third derivative evaluated at 0 is 2 times 3 times 1 minus 0 to the -4, which is 2 times 3. We'll do one more derivative and then hopefully the pattern will be clear when I explain it. So the fourth derivative, we have 2, we have 3, we have -4, but again, that will, when we apply the chain rule, get multiplied by a -1. So 2 times 3 times 4 times 1 minus x to the -5. So the fourth derivative at 0 is 2 times 3 times 4, 1 minus 0 to the -5, which is just 2 times 3 times 4. So the reason I'm writing it in this dumb way instead of just multiplying it out and saying 24 is because I want you to see that the pattern here is actually, if I'm here I block the board. Okay, there we go. Is actually just the factorial. So 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, 4 factorial is 4 times 3 times 2 times 1, and so on. So what we're getting is that if we look at the nth derivative evaluated at 0, we end up with that equaling n factorial, and we have to be thorough and state that this is for n bigger than or equal to 0. So let's take this information and plug it into our formula for the Maclaurin series up here. So what we found was that the nth derivative was n factorial, and that was really the hard part of this particular question or example. Because we have an n factorial on the bottom, we found out that the top is also n factorial. So it's just n factorial over n factorial times x to the n, which those just cancel each other out, and we have that. Okay. There we go, I got it. N equals 0 to infinity of x to the n is the Maclaurin series. You might notice that I didn't write that this equals the function 1 minus x to the -1, even though when I did the cosine example, I wrote equals. I'm just telling you this is the Maclaurin series because it doesn't equal the original function anywhere. It just equals it within the radius of convergence.